Thank you for joining us today in this session. We have a very special guest session today by Haihao Shen. He's a senior AI architect in DCAI, AISE at Intel, and lead model quantization and efficient inference for large language models on Intel platform. And in this talk, he will be talking about large language model quantization and efficient inference based on Intel extensions for transformers. Thank you very much, and over to you.
Okay,
Uh, you-
so thanks for the introduction. Um, so shall I start?
yes, you can start.
Okay, sure. Thank you. Let me share my screen. Um, okay, great. So happy New Year to everyone. My name is Haihao. Um, it's my honor to be here to present efficient LLM inference on CPUs. And thanks again to the Cohere AI for giving the opportunity to have this presented at the beginning of 2024. Okay, so before I'm showing something about technical, I will give a brief self-introduction about myself. I joined Intel at 2010 when I got master's degree from Shanghai Jiaotong University. You probably know this university. It is pretty close to Intel Shanghai site, and it's only about 2,000 steps between my school and the Intel. After joining Intel, had a chance to work on Houdini project, meaning do some binary translation from um, ARM to x86. When at that time the mobile application and was quite popular, so Intel has this Houdini project. After that, I started working on the DaVinci and automatic um, um, software project based on AI, actually computer vision technology to play the mobile applications automatically, like some Flappy Birds and Temple Run. At that time, it's pretty popular, I think. After that, I started work on the AI project Intel Cafe. I think Cafe is the first deep learning frameworks. So at that time, we started optimization for Cafe framework on Intel platforms. And then later, starting from 2020, I created Intel neural compressor, a low precision library and tool to support the model quantization. And now definitely we're covering the LLM quantization and the sparsity. And meanwhile, we create Intel extension for transformers since 2022 to demonstrate the performance with this low precision and the sparse model Intel platforms. So this is my journey, working journey. So yeah, and I post my Twitter and the LinkedIn. So if you have some question, you can also post. Okay. So before going to the like technical detail about efficient LLM inference on CPU, I would like to have give a quick introduction about neural chat. I think some already mentioned this beginning. So neural chat, we start like fine tuning work based on the mixture 7 billion model. So we have two steps basically. One step is supervised fine tuning, and the data set is open source to leverage the Slam Orca data set, and we tune the hyperparameters because like we need to apply LoRa. So how to apply LoRa and which layers should be applied LoRa. So there's some hyperparameters tuning here. And after that, we create a data set for the DPO. As you may know that this is the simplified solution to doing some alignment compared with the traditional reward-based IRHF solution. So with this data set and also the necessary hyperparameter tuning, so we're able to create our own 7 billion model and rank the top one in November 2023 last year. So if you can see that the Hugging Face open leaderboard, so you can see the neural chat version, V3 version, actually ranked at top at that time. And it's also great to see now the top models either leverage the model, neural chat model we released, and they do some merge or continue fine tuning, or they leverage some the data set we released before, like we call it DPO data set. And all this fine tuning and DPO is all based on the Gaudi 2 8 cards. You only spend like less than the 2 days to just one node to complete all the fine tuning stuff. Yeah, I also give some snapshot about the community response and also the adoptions by like Olama and also the other popular ML platforms or tools. They already adopt neural chat 7 billion model we created, and the lots of the discussions on the social media and also the other like blog. We participate in all these activities and together with the ecosystem users. Yeah, so Intel is now bringing AI to everyone. So, for example, starting from the agriculture, so Intel has the Getty project based on OpenVINO. They leverage some computer vision technology and make the help the to improve the yield and productivity of the prompts. And also, Intel has the mobile AISE, which is the one of the leading company on the autonomous driving, which is helping the transport. And also, there are the other domains actually leverage AI pretty much. And the most exciting one, I think, is since from last year, the generative AI, generated contents is the one of the top usage. I believe everyone may already have tried some, like Stable Diffusion, like ChatGPT. So I believe that with AI, more and more like AI technology will be like really touch your daily life. Okay, so how to support like AI, at least for Intel, we have the AI software stack here. So basically we have 3 stages. So from the data, and we based on the engineering data, we create a model based on the frameworks, either the traditional one or deep learning ones, and then the optimize the model and do the deployment. So on the data set, on data engineering part, we have the modern panels and the NumPy, NuBa. It's all like Intel optimization has been upstream to the stock version, or Intel release their own optimized version to help those the users to migrate the original code to the optimized version smoothly. And for the creating model, basically leverage the deep learning framework like PyTorch, TensorFlow, and also there are the other tools like SigOpt, which is can be used to do hyperparameter fine tuning by leveraging the AutoML, and also the neural compressor is one to quantize make the model smaller and run efficiently on the target platform. Of course, like Onyx runtime, OpenVINO, and there are ML as all the other alternatives to as the deployment alternatives. In the middle, you can see there's one API layers. There are many great products on the one API actually. I think the most popular one is the 1DN usually. One API Deep Neural Network Library, short name is 1DN, and also the 1CCL, Collective Communication Library, and 1MKL is one API Mass Kernel Library, and of course the about the data analytics we call DEL. And underneath, you will see that all the different ubiquitous hardware from cloud. For example, we have the Xeon. We recently launched the 5th generation of the Xeon, and we also have the Gaudi, as well as the Intel XE architecture like PVC. Of course, the client's workstation, definitely the other big pieces of all the hardware we can access, and also the edge. At the right side, you can see there's the develops like for AI, and Intel provides the IDC Intel Developer Cloud, and for people to try and experiment their model, their data on the latest Intel hardware and software. And of course, the Converge IO provides all the full stack ML platform so that they can easily build their applications and leverage all the underneath software and hardware. Hugging Face definitely is one of the top ecosystem builders, and Intel is actively working with Hugging Face to upstream the optimizations, the optimization recipe, fine-tuning recipes, and also the optimized model to Hugging Face models. Now, I will give the introduction about Intel Neural Compressor. As I mentioned earlier, I created this project in 2020 because at that time, there is the requirement to demonstrate the in the hardware. At that time, it's VNI. You probably know that, and we need to get the quantized model that can meet accuracy. So this is one of the motivation we create the Intel Neural Compressor. Now it has been developing for a couple of years, and we are now adding more features. So this slide actually shows the basic features and also what can support by Intel Neural Compressor. So you can see from the for the popular frameworks like PyTorch, TensorFlow, and the Onyx runtime, Intel Neural Compressor can support the basic model quantization technology, either the post-training quantization or the training as well, on the Intel platform, like from CPU, GPU to Gaudi. And we already validate the model quantization, more than 10K models, including popular, for example, the most recent one, Mixture, and also Llama 2. Of course, the traditional ones like Resident 50, Bird, are all covered by this bunch of models here. And also we have the accuracy aware tuning approach so that we can get the model to reach the SOTA accuracy through the auto tuning approach, and also the other technology like we have applied, for example, the pruning, sparsity, and distillation. So so you can see overall we have 3 big chunks of the compression techniques. One is low precision. Usually we'll see like Int8 is the most the popular one, I think. And now to accommodate the memory requirement to run LLM models, so 4-bit like Int4, FP4, or NF4 actually is getting more attentions. So that's definitely Intel Neural Compressor support this 4-bit quantization. And for the traditional one, I think BF16 and FP16 also in the scope. And now with the Gaudi, we have FP8 support as well. So regarding the pruning and sparsity, we also support different structure patterns. For example, we have the blockwise with NM and NEM pattern, which is like the what NVIDIA they proposed. And also we have the channel-wise sparsity pattern. So of course we have the unstructured pattern, like one actually it's one per, one by one. Usually we call it one by one pattern for the unstructured sparsity. The most recent one, I think, sparse GPT is the one of the popular approach to achieve this unstructured sparsity. I will mention the those technology in the following slides. Distillation, I think, is the other dimension that we can apply the model compression, and even they can combine with the previous low precision pruning sparsity. Usually, we can leverage this technology to distill this much smaller model, either through the two models. One is the big one, or the other is smaller one. Or we can leverage some self-distillation, which we called on the same model, which means the like the teacher model will be the FP32 model, while the student model can be Inter 4 or Intel model. Yeah, here is the software architecture of Intel neural compressor. Basically, we have several layers. Underneath is the hardware and also the supported backend, as mentioned earlier, for PyTorch, TensorFlow Onyx runtime, as well as the Intel extended frameworks. For example, the Intel extension for PyTorch is also in our support list, and it is easy to create another custom backend with the exposed API by Intel neural compressor, so that if you have a new backend, for example, your new inference engine may not based on like any framework, you can also easily create such low precision support for this new backend. In the middle, it's a core part for the Intel neural compressor. Basically, we have the compression algorithm here. For example, for int8, we have the SmoothQuant, which was originally proposed by MIT, and also the int4 algorithm. For example, the GPTQ or AWQ, or the our own algorithm like AutoRound. I will cover this in the following slides. Of course, there are the other utility function like model export, and also the accuracy aware tuning strategies, so also part of the core here. There are also the tensor inspect, which can track all the tensor statistics, for example, the activation or the weight, so that we can apply different quantization recipe to the tensor. And on the top, you will see the different front ends, like in INC, we usually call it INC based API. Of course, there are the other zero code API, which means you just run one like a notebook based solution, and the quantization code will be automatically generated. Also, there's some debugging tool we call Neural Insights. Will give you the hints how you can tune this model to get the better accuracy. Then we have all this technology. We have the compressed model as our examples, and people can can take this compressed model and build their application. For example, for LLMs, definitely it's a chatbot or some co-pilot, so they can directly leverage all this application to build their service as well. Now, yeah, I mentioned the SmoothQuant, which is one of the great algorithm for the int8. As you may know that for LLMs, they have the outliers in the activations. If you're familiar with this area, so you probably already know from some research paper, they already mentioned this. And it's true for same as like what we observed in the LLM models. And the traditional int8 recipe usually requires to like for the activation, they apply per tensor quantization, and for weight, they can apply either per tensor or per weight quantization, while it does not work anymore for ARM activation because there are too many outliers. So having only one scale for the entire tensor will make the others uh, lose accuracy. So just like uh, the diagram here in the left part, you can see this is the activation distribution. For certain channels, actually, there's many outliers. And the right side, you can see the idea is like the shifting the activation outliers to the weight. Uh, some intuitions is like we have this some formula like 1 times 100 equal to 10 times 10. So if we have those outliers, why not that we shift some outliers strength to the weight, so that for the weight we already have the per channel, so we can we can still work well uh, for the weight quantization, while for the activation we already make this not that outlier, right? So we can still apply the potential quantization, but we can preserve the overall the accuracy. So this is the basic idea why SmoothQuant is getting popular in our models. So for this int8, actually, especially useful for the first token generation, because for the typical like low precision for weight, they still leverage the high precision, for example, the 16-bit for the activation. So this will give the may not be the best performance on the first token, while SmoothQuant actually is pretty good and balanced for both the first token and the next token generation. Okay. Yeah. So this is more like what Intel has done. The enhancement to the original SmoothQuant algorithm. So basically, we support the automatic fine tuning. Operator-wise, that's SmoothQuant alpha tuning. So originally, I think the implementation only covered the global level. So which means that the smooth alpha is not only applied to all the layers. Now we are able to tune each layers with different smooth alpha value, and it's really helpful for the recent error models. I think, especially for Llama 2 series model, it requires the per layer tuning for alpha. And also we support different fusion patterns because you know that for SmoothQuant, you probably need to insert some mal to make the formula like original the model preserve the mathematical equal. So those multiple operators need to be folded or fused into the previous layers. So that's why we enhance this a bit. The third one is we expand the operator coverage actually from linear to more operators like MATML. And finally, we productize the SmoothQuant for multiple frameworks, including original one is PyTorch, and we extend to TensorFlow and Onyx runtime. And the work we have done for Onyx runtime has already been upstream to the community. So this is the chart to show the accuracy comparison between int8 and FP32. So basically for the blue bar is the AP32, and for the red one is the intent with SmoothQuant. Maybe it is a little bit small here. I've listed most of the popular LLM models. So, but you can have a overall feeling that for the Intel 8, they still keep the very close to the AP32 and even better than the original one. Because for the calibration, you probably have the chance to figure out the optimal scaling factor that can even better than the original. But this definitely is not the typical one. So you can see for the majority, Intel is a little bit lower than the FP32, but still within the 1% relative loss, which is typically the acceptance rate from our customers. Okay. So this is the special case for the Intel stable diffusion. There's some background here. Is like we fine tune the stable diffusion um, to make the model recognize the word. For example, deco. In the prompt, you can see a lovely deco is the special word that we fine tune the model to recognize this. So with this fine tune model, we apply intent, and then you can see that for the intent model with the same prompt, you can see the overall the image quality is pretty good, and we also contribute the recipe and also the optimization to Hugging Face optimal Intel and also diffusers library. Yeah, so this is the about sparse model. I mentioned earlier that Intel neural compressor supports three big chunks of the compression techniques, and sparsity, pruning sparsity is the definitely one of them that we supported, especially for the reason for error models. I think you probably know the sparse GPT, which actually is um, share some great insights of how we can do or sparsify the error models. So we actually did similar things and implemented sparse GPT algorithm in Intel neural compressor, and we listed some of the models and give the accuracy comparison here. For example, for um, the larger size error model, for example, the 70 billion Llama 2, you can see that um, the accuracy between the dense model and the sparse model uh, is negligible. So accuracy is very close to the original dense one. And more importantly is the sparsity ratio can reach 60%, which is pretty good, which means that you can uh, further apply the other technology like Intel 8 or Intel 4 to deliver a joint performance gains with a sparsity. So usually for error model, you know that it is more like for the memory bandwidth um, issue during the next generation. So as long as you can make the model smaller or load less data, then you will get performance benefit. Um, Similarly for the other smaller one, um, you see that the overall spiral ratio is lower than the large size one, as um, this is a little bit intrusive that for the larger one, usually we expect some redundant parameter that may not work, so we are able to prune this weight. But usually for the smaller one, um, the weights are becoming more important and less chance to get their pruned. So that's also our data actually support this all these assumptions. Okay. Okay. So we are now go to the Inter 4. This continued popular, I think, for Inter 4. There are lots of great work in the community, in the industry, and academia. So we also did some work for Inter4, especially the recent one we call sign round. This is the recipe we invented, and the basic idea is basically for the int4, usually we have the floating point, right? And we want to convert to the integer. So how to convert it? We need to get the scaling factors and then apply some round, right? But we don't know what kind of round is the best one. For example, do we need to round up or round down, or I don't know, the different rounding um, policy may lead to the different result. So that's the motivation for us to apply a sign round. We can have the fine tuning, kind of fine tuning flow to decide whether for this one we need to apply the round up. For the other one, probably we need to apply the round down. So that's the idea. So finally, we see the overall result is pretty good, and um, the result on the popular element, we show that um, more than 85% uh, better than the GPTQ, and more than 90% of the all the test case, the sign run is better than AWQ. And I posted the link about our paper on archive, and also you can scan the QR code to get the link as well. Okay. Yeah, this is another diagram showing the accuracy of Inter4 error models compared with IP32. Similarly, like the intent diagram I showed before, this is measured by Llama or OpenAI dataset, a Lambda OpenAI dataset, and this covered the most popular error models, and you can see whether your favorite ones are on it or not. Basically, we can see the Inter4 models. The average accuracy is uh, pretty close to the FP32. While here, I want to mention that for the activation, it is the high precision like BF16 or FP16, different from the Intel SmoothQuant that we introduced before. Okay. We will publish all this recipe to the Intel neural compressor, so you can find the recipe and reproduce the data, just following the document we released. Yeah, so in previous slides, I briefly mentioned the Intel neural compressor, which can produce the compressed model. And now we need another library, another tool to demonstrate the performance. Otherwise, the model is becoming smaller, but still you did not get the performance benefit. Now you can have it with the Intel extension for transformers. So this gives you the some initial feeling of how we apply Intel extension for transformer and get the performance benefit. So basically, this project extends a target phase transformer API for efficient low bit inference. So given an example here, we just added 2 lines. One is that we import Intel extension for transformers, and use the auto model for cache language model class, and the other one is we just use this auto model for cache language model and use the add one parameter we call load in 4-bit. That's it. So you can get the performance benefit from this sample code. And here we use the NeuroChat 7 beta model we mentioned in the beginning. So basically, for any catch language model, as long as it can run well on the standard transformer APIs, now you can smoothly migrate to use Intel extension for transformer and get the performance benefits on Intel platforms. Okay. So what's the technology we applied in the Intel extension for transformers? So first we have automatic quantization flow. So this is actually built on top of the Intel neural compressor mentioned before. So the input model is the FP32, and we have different recipes for Intel4 here. For example, we support sign round, and we also have the others like GPTQA, WQ, and RTN. So we'll apply different recipe and we'll evaluate the Intel4 model on the interested data set. For example, Lambda OpenAI, and we'll get the accuracy. So if the accuracy can meet the target, for example, 1% of loss FP32, then we exit the loop and get in the full model. Otherwise, they will traverse the different recipe and get the best one. So once we have the interval model, we pass to the AM runtime, which is the runtime on the Intel extension for transformers. And internally, we have the auto kernel selection based on your target machine. For example, based on your AISE, and also the data type you specify. For example, for the different maybe weight data type and also the compute data type, then the kernel can do it automatically. Also for the different quantization data types, like int8 and also int4, FP4, or 1F4. This is all supported right now. Okay. Yeah. So this is the simplified diagram for the efficient error runtime on the Intel extension for transformers. So inspired from the work from the work on llama.cpp. Actually, we also support the GGML and the GGUF, two different formats, aligning with the llama.cpp. We recently add the tensor library for the low precision gems, which is pretty efficient to run the weight only 4-bit gems for the large language models. So this is in the middle, the green part for CPU tensor library, and also we have the error optimization for error models. For example, the indirect access KV cache, basically to reduce the memory bandwidth, and also we optimize the post-processing part to fuse several small ops to the bigger one. Now, of course, there are the basic components for the ARM runtime. For example, the memory management. So how to allocate and deallocate the memory, and the threading scheduler, as well as the other optimization and fusions. On this, we have the hardware abstract layer, which is dedicated for CPU right now, but it is easily extended to support like GPU or the other platforms. Okay. Now we come to the low precision gem part. As mentioned, this is the automatic kernel selection. So right now we support different computer type and also the computer AISE. So this is all like based on Intel CPU. So you can see for the input and output. So the data types covers the FP32, FP16, BF16, and the computer type you can also based on your AISE, you can do the best one. For example, we have the VN9, then we definitely can consider the computer type int8. And also for the most recent AMX instruction, we can consider the intent and also BF16 by leveraging the AMX instructions. So this also gives all the alternatives once you have the like Xeon, even the not the latest Xeon generation, but still you will get the decent performance against by leveraging the interval weight only interval quantization and using the Intel extension for transformers. Okay. So this is about the performance. So as I mentioned, the Intel extension for transformers actually is compatible with llama.cpp, and we added, we leveraged the CPU tensor library, so we're able to get better performance, on this large language models. So you can see from Llama 2 to the like Dolly V2, this smaller or small sized or the middle size of large language models, we're able to demonstrate up to like 2.5x better performance than the original llama.cpp, and we plan to contribute the optimization and upstream to the llama cpp gradually. By the way, this is all like measured by um, the second token, next token, with the input token length as 1K on the Zephyr Rabbit, our fourth generation Intel Xeon processors. And if you want to get more details, either the accuracy or the performance, you can also visit the blog we already published on highly efficient LLM inference on Intel platforms. So we already talked about Intel neural compressor to quantize model, to compress model, and we also cover the Intel extension for transformers, which provides the transformer-like API to demonstrate the performance benefit by the model quantization or model compression. So you can see that with the ubiquitous hardware and the open software, and of course the open source models, then we can democratize generative AI with all these technologies. Especially for the open software part, you can see we have the stock version, for example, PyTorch. We also have the Intel extension for PyTorch, which actually serves the cache to get all these optimizations gradually upstream to the stock version. Similarly, we have the Hugging Face transformers, and we have the Intel extension for transformers, as well as the deep speed, or the popular frameworks for large language model distributed training fine tuning. So we also have the Intel extension one, and also the like fast regs, mainly for the retrieval augmented generation based on the haystack. And on the top, you can see all these the popular language models, stable differential models, and also the most recent fine-tune model we released to the community as well. Okay, so now we come to the summary page. So as mentioned earlier, that we pretty covered the three pieces of one is the model we mentioned. It's NeuroChat 7 billion model from Intel, and also the Intel AI software portfolio, which pretty covered the three stages from engineering data, model creation, optimization, and the deployment. So you can scan on the QR code to get the model. Of course, in the second part, we covered the Intel neural compressor for the LLM quantization, and the last one is the about Intel extension for transformer to demonstrate the performance of LLM inference on the Intel platforms. So basically, we have all these three parts covered, and I think I can leave like 10 minutes for the Q&A. Any questions on the line? Happy to take your questions.
Hi, good session. I have a question. So, do you have any study on like what is the largest model size uh, which can on which you can perform the inference on Intel CPU? So, for example, can you use like a Falcon 180B and quantize it enough to like
Mhm.
do an inference on CPU?
Yeah, so I think so. Um, for the CPU side, right now with the current technology, of course, like we have the some advanced one like a tensor parallelism based on the deep speed. We can do the inference of LLM inference on like 13 billion or even bigger one, as long as we have the right um, the latency target. So it's pretty efficient to run like 30. I think middle size the large language models as already we demonstrate in our previous blog. Um, but for the larger one, for example, more than 100 billion model, I would suggest we can consider like the ubiquitous hardware Intel is now providing, like for example the Gaudi 2 or the PVC. They can actually themselves have the more memory bandwidth or the computation um, computation more power on the computation side and the memory bandwidth side. So you can also try these two like hardwares Intel is providing. Are there any plans for working on early exit networks? Uh, yeah, so for early exit, especially for the ARM models, we actually we're adding this feature collaborate with the Intel Labs. Um, So I think for the Intel neural compressor tool, we already had some early work on the early exit, but we're continue exploring the other different algorithm regarding with the early exit networks. So if you see like the paper we published in last year, the NeurIPS workshop about the efficient language models, you can find our early paper. So I can maybe post some link later so you can find more information there. Um, Another question I saw is Intel purpose-built hardware available. Yeah, I think I mentioned the Intel Developer Cloud IDC it already provides all the latest hardware in Intel is provided. For example, the Gaudi 2, which is the accelerators, right? And also have the GPU like Intel XE. So you can try get access to the IDC, um, then got the system and run your experiments on the IDC. I also see another question is about can you please share the reference source resource link scientific paper? Okay, yeah. So um, Amanda, I think we can post all this information later, right? I mean,
Yeah,
uh, show all these links, and I will provide to you, and so you can help to maybe share with more audience here.
yeah, I will show you.
Okay, sure. Thank you. Okay, so someone asked questions about the sign round. Yeah, so actually there are two questions. One is this how to leverage sign round, maybe some technology for the model compression. The other one is for the model serving part. So let me answer the first question. So yeah, for the new algorithm, right now we want to provide the transformer-like API, just like transformer already integrates the recent quantization algorithm, for example, auto GPTQ, and also for the AWQ. I think we plan to deliver the similar experience, like only minimal change to the transformer API. They can easily get the benefit of our new algorithms as well. So this is what we plan to do. And the other, like for the model serving, I think we already started some work and upstream into optimization to the TGI and also VRMM. So probably we'll have more optimization soon available on these two the popular serving frameworks. And I see also questions, what might this change in terms of on-device model? Um, um, we did not yet touch a lot about on-device models, but basically the compression technique we are exploring can be applied to the on-device model. For example, the combination of low precision, sparsity, pruning, distillation, even we can get a much smaller model with the on par performance with the much larger size the language model. Um, and one interesting example is like recent from Microsoft. They released Phi 2, which is only like more than 2 billion model, but showing the pretty good performance compared with the other maybe 30 billion model, even bigger one. So I believe that for the smaller one, smaller model will be uh, very interesting in this year, and we're expecting like more on-device models running. For example, most recent Apple, they have their own framework and running their models as well. Okay. I think I pretty covered all the questions posted on the chat window. So yeah, thank you. I'm gonna posting on all this great informations timely. So one question is why API open window while working on these projects? Yes. So as mentioned earlier, that we have the optimization, but the upstream work is not like one shot. So sometimes the upstream may take some time. For example, some creative features, maybe like even longer. So we expect for the customers, if they want to try these features before the stock version, they can try the extended one. But gradually, we will upstream all this optimization to the stock version so that people can just get the best out-of-box performance, out-of-box experience and performance by just getting the stock version. So that's the mainly the motivation of why we created some Intel extension or Intel projects, but finally you will get most of performance from the stock version. Another question: so algorithm types adapt for this project? I'm not which project here. It's a neural compressor or it's a extension for transformers, but assume this is the neural compressor since it's mainly about the algorithm. So if it is true, then so basically we cover the most recent popular algorithm for AI models, spanning for like all three types I mentioned before. One is the low precision, the other one is the pruning sparsity, and the last one is the distillation. So as long as can meet these three main aspects, we actually are very open to take the new algorithm from the community. Of course, besides these three, early exit, and also the other technology we are also exploring, and we are not limited to only like 3 compression approach, but that's the main basic algorithm I want to say. But for the other one, we are also considering this to expand the compression algorithm here. Oh yeah, you posted lots of questions here. It's what different software is used for this project? For the Intel neural compressor, I think the algorithm part, and also as mentioned for the backend, it supports the different hardwares like Intel CPU, GPU, and Gaudi. So for the Intel extension one, we're now mainly focus on the CPU part, but we plan to extend a little bit to support GPU together with the Intel extension for PyTorch, which is already supports GPU, Intel GPU. So we're working with the right people to get the optimization available, publicly available for Intel GPUs. Now the question: what's a different metrics measurement? Yeah, in general, the match criteria is like relative 1%. So this is what we got from the our customers, but still it is not the single rule does not fit for all the customers. So for some customer, they may even like require even more strict accuracy target. For example, 0.5 or even 0.1% accurate loss. So it quite depends on the customer and also data set and model itself. Yeah, I think now I think I finished all the questions on the chat. Okay.
If we don't have any more questions, we can end the session.
Yeah.
Thank you very much. It was really an insightful session.
Okay. Thank you, everyone. Have a good day and night. Bye.
Yeah.